Okay, good afternoon everyone. So this is the 9th week. We are meeting for the course Fluid and Particle Mechanics. So in the last uh, meeting, we mostly talked about the statistical description of the turbulent flow, where we discussed the time averaging, space averaging, and the ensemble averaging. So time averaging, if the turbulent statistics are not changing with time, then we call that it is stationary turbulence. If the turbulent statistics are not changing with space, then we call it as homogeneous turbulence. And the ensemble average is actually what we do in real life. That's an collection of independent realizations of a random variable obtained under identicals, initials, and boundary conditions, and then an arithmetic average of those is called an ensemble average. And then we prove that the average of an fluctuating quantity is always zero, whether it's an ensemble average or the time average or the space average. That is true for any averaging. Okay, and then we talked about that, like what are the different central measure of turbulent fluctuation of the fluctuating velocity field in a turbulent flow, and these informations about the fluctuations can be captured in terms of the variance of velocity, skewness of velocity, and kurtosis. Okay, and then we discussed that not only the moment of the turbulent fluctuation velocity is important, but also the correlation of the fluctuating velocity component with itself or with or the velocity in the x directions, y directions, and z directions, how they are correlated with each other. That will also give some important information about the nature of the turbulence flow. And then we mostly discuss that how that autocorrelation coefficient is related to the turbulence energy spectrum. Now in this week we will thoroughly derive the one important thing is called a Reynolds. So we'll first talk about the Reynolds averaging process, which is applicable to any like a equation which gives a stochastic result. You can average that equations using the Reynolds averaging process. So for that you can decompose the quantity into its mean and fluctuations, then put that into the governing equation, and then average it out. Okay, and this process is called the Reynolds averaging process. So we will derive the Reynolds average Navier-Stokes equation. Okay, so we will mostly derive the Reynolds averaging Reynolds average Navier-Stokes equation, or we'll call it as RANS. Okay, so before going into the details, mathematics and all, let us first see that why we need to average first of all. So the Navier-Stokes equations, so the one thing which I need to be very much clear is that the Navier-Stokes equations is very much valid whether the flow is laminar flow or the turbulent flow. In case of laminar flow, let's say in a laminar pipe flow or flow through a channel, etc., you can analytically solve the Navier-Stokes equation, but in case of turbulent flow, you can't solve it. Okay, but in case of turbulent flow, the Navier-Stokes equations is valid. Okay, it's not like that the Navier-Stokes equations is not valid. So NS equations are very much valid for the turbulent flow. However, because of the multiple length scale and time scale in the flow, it will give a stochastic solution. Okay, and there will be a lot of uncertainties in the solution due to the strong dependence on the exact initial conditions and the boundary condition. Moreover, it is very difficult to solve numerically because of the fact that your numerical strategy should capture all of the time scale and the length scale, and it is a very tedious job to do computationally. However, one can do that, and it is possible to do through like using the computational strategy, what we usually call as the direct numerical simulations. That means you can solve the Navier-Stokes equation directly. Okay, so but so the intuitions is like that, then it has the solutions of the Navier-Stokes equations is giving an stochastic result. So if I average it out, I might get a result which is not stochastic. However, you can do that, or actually we can do that through this averaging process, but there is also a problem. What is the problem? So if we average the NS equations statistically, it will give deterministic solutions. There is no doubt about that. But the problem is that when you will average it out, then the number of unknowns in the equations will be more than the number of equations. So the equations are not closed, and it is known as the turbulent closure problem. Okay, so before going into the details of that, let me like average it out. So we'll first write down the continuity equation, and I will derive this using the tensorial notation, so it will be not that difficult and all. So I will first write down the continuity equation. So continuity equation is dou uj dou xj is equal to 0, where this j is from 1 to 3. Okay, so that means it is the summation. So it is like that dou u1 dou x1 plus dou u2 dou x2 plus dou u3 dou x3 is equal to 0. Okay, where j is equal to 1 2 3. So I am in the tensorial notation, I am writing it in this way, where dou u1 dou x1 is actually dou u dou x, dou u2 dou x2 is dou v dou y, and dou u3 dou x3 is dou w dou z, which we known as the continuity equations. But so like it's very simple, so I will not write it down. So here the j runs from 1 to 3. So these equations itself represent the continuity equation. So I will call it as equation 1. And the momentum equation. So what is the momentum equation in terms of the tensorial notation. So in terms of the tensorial notation, you can write it in this way, that rho multiplied with dou ui dou t, which is the temporal term, plus uj dou ui dou xj. Fine. Okay, everything is multiplied with rho is equal to minus dou p dou xi plus dou xj of mu into dou ui dou xj. As simple as that, and I will call it as equation 2. Fine, there is no doubt so far. So now what I will do is that I will write that ui or uj, whatever you can write, ui is equal to ui bar plus ui prime. That means I am decomposing the velocity into its average and the fluctuation term. These I will write it as equation 3, and these indices I is like I can, like, instead of I can write j, I can write k, so anything I can write. So thus now I will put equation 3 into equation 1. Okay, so what we will have? We will have dou uj bar dou xj plus dou uj prime dou xj is equal to 0. Am I right? There is no doubt about it. Let's call it as equation 4. Fine. Now I will average it out. Averaging equation 4 statistically. So what we will have? So we will have dou uj bar dou xj plus dou uj prime dou xj whole bar is equal to 0. Now I can split this bar and write the individual bar. So bar equal to 0. Okay, that means, so now one important thing which we need to remember here, that the differential operator and the averaging are commutative. That means that dou xi some quantity a bar is equal to dou a dou xi the whole bar. I can write it. Okay, fine. So I will use this property here, and so if I use this property here, what I am getting, that dou uj dou xj whole bar then another bar plus dou uj prime bar divided by dou xj is equal to 0. Am I right? That means what? So this quantity, average of an average, so it will be the same quantity, right? There will be no like average of an average will give me the same averaged quantity, and then by the commutative plus what is this quantity? This quantity is 0. Am I right? This is 0 because the average of a fluctuating quantity is always 0. So that means, so what I am getting from here is that the averaged equation, so the averaged velocity also obey averaged, like the average velocity also obey the continuity equation. Okay, so that means dou uj bar dou xj equals to 0. Fine. Now, so in equation 4 I have dou uj bar dou xj plus dou uj prime dou xj equals to 0, and in equation 5 I have the first quantity is 0. Okay, that means thus from equation 5 and 4 from 3 and 4 we can say that the fluctuating quantity also obey the continuity equation. These I will write it as equation 6. So far I think it's very much clear. So by the averaging process of the continuity equation, I showed that both the averaged quantity and the fluctuating quantity, or the average velocity or the mean velocity and the fluctuating velocity, both obey the continuity equation. Okay, so this is what I get from continuity equation. Now I will do the same exercise for the momentum equation. Okay, so what I will do here, so I will put equation 3 into equation 2. Okay, so putting equation 3 into 2, so what we will get? We will get that rho, what is the first term? First term is dou ui dou t. That means we will get dou ui bar dou t plus dou ui prime dou t plus, what is the second term? Second term is dou ui dou xj. So for dou ui I will have dou uj bar plus dou uj prime into dou x j of dou ui bar plus dou ur prime. Fine. So far there is no problem. So this is the left hand side of equation 2. What is there in the right hand side? Right hand side I will have, so similarly I will decompose the pressure also in a average quantity and an fluctuating quantity. So I will have this minus this P prime is the fluctuating quantity. Okay, so this P prime is the fluctuating pressure, P bar is the average pressure. Okay, so I can, so like velocity, like I decompose the velocity into its average and the fluctuating component, I can write the pressure also in its average and its fluctuation component. That's all. That's what I did here. Okay. Plus now I have the last term. What is the last term? So it will be dou xj of mu into dou ui prime dou ui bar dou xj plus dou xj of mu into dou ui prime dou xj. Okay, that's all. So there is no confusion in it, it's all fine. Okay, now averaging, so I'll call it as equation, let's say this is equation 7. Now I will average equation 7 statistically. Okay, averaging so what I will get if I average this equation statistically. Okay, so that means what I am doing, I am just averaging this quantity, that means this is the over bar I am writing here, averaging this quantity, averaging this, and averaging this. So let me write the individual averaging process. So individual quantity, so what the first quantity will be? So the first quantity will be, so dou ui bar dou t whole average is equal to dou ui bar dou t. It will be the same because the average of an averaged quantity is the same quantity. The second is dou ui prime by dou t whole average is equal to dou ui prime average by dou t, and this quantity is 0, that means this is 0. Okay, similarly in case of pressure also, so dou p dou xi whole bar is equal to dou p bar dou xi, and dou p prime dou xi whole bar is equal to dou p prime bar dou xi, and dou p prime bar averaged of the fluctuating pressure is 0, that means this term is 0. Okay, so yeah, now what will be this term? What will be dou xj of mu into dou ui bar dou xj the whole bar is equal to what? So it is the same thing because this is an averaged quantity, and also the that average and the differential operator are exchangeable, you can exchange that. So that's why I can, let me write it down. So I can write it as dou xj, okay, mu into dou ui bar, the whole bar, divided by dou xj. I can write it. So and the average of an averaged quantity is the same quantity, so it is the same. So it is dou xj of mu into dou ui bar dou xj. Similarly, what is dou xj of mu into dou ui prime dou xj? So I can write it as dou xj, this is a bar, into mu into dou ui prime bar dou xj, and this ui prime bar is equal to 0. That means this is equal to 0. So for equation 7, what and what term is 0, I'll just cross it out. Okay, I'll just round it, like after the averaging which and which term is 0. So this term is 0, this term is also 0, this term is also 0, okay, and the term which I will and the rest of the term, like this term will be the same, this term will also be the same, this term is also be the same. Now I have to look only the one term. Let me look it, let me do that. So there only the interesting things are there. So what is that term? That term is dou uj bar dou uj prime into dou xj of ui bar plus ui prime. Is it the case? Yes. So what I can write it from here? I can write it as dou ui bar dou uj bar dou ui bar dou xj plus, so I have to do the average of this entire quantity. Okay, I am doing the average of this entire quantity. So this means the average of the first quantity plus what is the second quantity? Second quantity is dou uj bar dou ui prime dou xj bar of the entire quantity plus uj prime dou ui bar dou xj, the bar of the entire quantity plus uj prime dou ui prime dou xj, the bar of the entire quantity. Is that fine? Now let me individually write the each of these quantity. So first quantity is ui bar dou ui bar uj bar dou ui bar dou xj, the whole bar. Okay, So this uj bar is an averaged quantity, so I can pull it out from the average. So I can write it as uj bar, then dou ui bar dou xj the whole bar. Okay. And the differential and the average operator are exchangeable, so this term remains the same. Okay, because again the average of an average quantity is the same quantity. So dou uj bar dou ui bar dou xj. This is the fate of the first quantity, the first term. Now let me write down the second term. Second term is dou uj bar dou ui prime dou xj over bar of the entire quantity. Again uj bar is an average quantity, so I will put uj bar outside the averaging, and I have ui prime uxj the whole bar. And again the differential operator and the bar are exchangeable, so I can write it as uj bar dou ui prime bar divided by dou xj, and this ui prime bar is equal to 0. That means this quantity is 0. That means the the second term is also 0. Let me write down the third term. What is there in the third term? So third term is uj prime dou ui bar dou xj the whole bar. Okay, fine. So what I can write from here, I can write it as uj prime dou ui dou xj the whole bar and then whole bar. Is that right? Because this bar I can write it over the entire quantity, because the differential operator and the averaging are the commutative. Now this second part is an averaged quantity, so now I can pull it out of the average. That means I can write it as dou ui dou xj bar of the entire quantity into uj prime bar. Now what is the uj prime bar? Uj prime bar is 0. Okay, because the average of a fluctuating quantity is 0. That means this term, the third term, is also 0. Now let me come to the fourth term. What is there in the fourth term? So fourth term is uj prime dou ui prime dou xj average of the entire quantity. Okay, what I can write it here. So this term is definitely not 0. First of all, we need to recognize it, that the last term of this convective acceleration, the last term of this convective accelerations is not 0, which involves only the fluctuating velocity. So it doesn't involve any average velocity. Okay, so this term we can write it in this way also. So uj prime dou ui prime dou xj plus, can I write it in this way, that it is ui prime dou uj prime dou xj the whole bar. Okay, why it is this? Because this quantity this quantity is 0, that means it is effectively the first term only surviving, and just added a 0 here and wrote that 0 in this fashion, and I can write it. This term is 0 from where we know that from averaging of the continuity equation, that the fluctuating quantity also obeys the continuity equation. Okay, what I can write from here? So from here I can write that this term is equal to dou xj of ui prime uj prime the whole bar. Now the differential operator and now I can write the bar inside the differential operator. That means I can write it as dou xj of ui prime uj prime the whole bar. Okay, this I can write. Fine. So what I am effectively getting from equation 7, okay, so these red like these quantities which I encircled by red lines are 0 from the beginning, that we know. So what are the terms which are surviving? Let me write it down once. Okay, so the terms which are surviving, so equation 7 so after the averaging process, so after process, the momentum equation that is equation 7 becomes rho. I will have only the average for the time derivative, the first term, plus uj prime dou ui prime dou xj. This term is survived as the same, plus the other term which survived is the dou xj of ui prime uj prime whole bar. So this is what I got in the left hand side, and in the right hand side I have minus dou p bar dou xi plus dou xj of mu into dou ui bar dou xi. Fine, that is what I have as the final equation. I don't think there is anything wrong here. Okay, great. This I can write it in a different way, that is rho into dou ui bar dou t plus uj bar dou ui bar dou xj. That means this is the right hand side of the momentum equation that involves only the average velocity, okay, is equal to minus dou p bar dou xi, okay, plus, so 1 minute, so that I wrote it as equation 7. I will, okay, so this is dou xj of mu into dou ui bar dou xj minus what I have here is the dou xj of rho ui prime uj prime whole bar, okay. I will write it as equation 8. So that means after the averaging process we got equation 8. What is wrong in equation 8? There is nothing wrong, but we got an extra term which is this last term, which is the last term in the right hand side, okay, and this term has the dimension of stress. So the last term in equation 8 has the dimension of stress, okay. So let me write it down once again. So this rho ui prime uj prime whole bar has the dimension of stress, okay, and we will call this ui prime uj prime whole bar is equal to the turbulent stress or the Reynolds stress, because we got it by the Reynolds averaging process. So we will call it as the turbulent stress or the Reynolds stress. So this averaging process is absolutely fine. There is nothing wrong in that. And by the way, this is called the RANS. This is the Reynolds averaging Navier-Stokes equation. This equation 8 is called the RANS, okay. So dou ui prime dou ui prime uj prime whole bar has the dimension of stress, okay, and this is one of the important mathematical characteristics of this term, that mathematically it has almost perfect resemblance with stress, because rho dou ui prime dou uj prime bar also requires like the stress tensor two indices for its specification, okay. So that means I can write this last term like this. Let me write it in this way in tensorial notation. So what I will get here is that so this is with a negative sign and this is called the Reynolds stress. Sorry. Okay. So that means this minus rho ui bar, I can write it in this way, minus rho, what I will have is this. So this is, so I and j are 1 to 2. So what is the number of element in this stress tensor part? It will be total 9 element. What will be the first element when I equal to j equal to 1? So square. What will be the second element? u1 u2 both prime bar. What will be the third quantity? u1 prime u3 prime bar. Okay, when I equal to 2 j equal to 1, then that is u2 bar u1 bar this, then this is u2 bars u2 prime square. So there is no bar here, I am saying bar repeatedly, that is wrong. And this is u2 prime u3 prime whole bar. When I equal to 3 and j equal to 1 to 3, what will be this term? So this is u3 prime u1 prime bar u3 prime u2 prime bar, and this is u3 prime square bar. So this is how your stress tensor looks like. So this is the turbulence stress tensor. Okay, so you can see that there are 6 independent component. Okay, there are 6 independent component, and it is a symmetric stress tensor, just like the usual stress tensor we have, and this is known as the Reynolds stress tensor or the turbulence stress tensor. Because, like, why it is called the turbulence stress tensor? Because these stress tensors are originated from the turbulent fluctuations in the flow. Okay, so that means by this averaging process, I can now, if I solve equation 8, now I will get a deterministic answer. But the problem is I can't solve equation 8 unless and until I know the information about this stress tensor term. If I know this stress tensor term perfectly, then there will be no issue. Okay, then there will be no issue in knowing this quantity dou ui prime dou uj prime. I mean this last quantity dou ui prime dou uj prime whole bar. I need to know this quantity in order to solve equation 8 along with the continuity equation. Okay, and these continuity equations are equation 6 and equation 5. So the people who solve the Rand's equations numerically, they solve it via modeling this Reynolds stress tensor term. Okay, and this is where the turbulence modeling begins. I mean, the turbulence modeling is all about. Turbulence modeling is basically modeling the Reynolds stress tensor term. So turbulence modeling means the modeling of the Reynolds stress tensor term. That's all. And there are 2 ways of modeling this Reynolds stress tensor term. And by the way, this is called an turbulence closure problems in the turbulence, because as you can see that I have, so how many number of equations I have from here? So from I equal to 1 to 3, I have from equation 8 I will have 3 equations for the 3 velocity component. Okay, for I equal to 1 to 3 and j equal to 1 to 3, for I equal to 1 to 3 I will have only 3 equations, and I have also one equations for the continuity equation, that is equation 5. So I have total 4 equations. one continuity equations and the three momentum equations. So the continuity equations is also for the average velocity, the momentum equations is also for the average velocity, the three momentum equations. However, I don't know the information about this Reynolds stress tensor term. Okay, so that means I don't know the informations about this 6. So in order to solve equation 8, I need to know the information about this 6 independent quantity which are involved, 3 diagonal quantity and 3 off diagonal quantity. That means I have 6. So that means I have 4 unknown, 3 average velocity, that is u1, u2, u3, the bar of all that, and the pressure, average pressure, that means the 4 quantity, plus here I need to know 6, that means total 10 unknown quantity I have. Okay, including the continuity equations and the Rand's equation, but I have only 4 number of equations, so that means it is not possible to solve, and this is typically known as the closure problems in the turbulence. And that is where, in order to close these equations and then solve numerically, you need to model this stress tensor term. So one way of modeling this stress tensor term is so I'll just not go into the details of all that. Through the turbulent viscosity modeling, one way is the turbulent viscosity okay, and the two term is the Reynolds equation, Reynolds stress equation. So let me check it once, the names are correct or not. So this is where these are the turbulence modeling actually. Yeah, that means a turbulent viscosity or a mixing length model. Okay, a mixing length model. And the Reynolds stress model, I guess, and the Reynolds stress model. These are two popular method for modeling the Reynolds stress tensor, and then using that you can solve the average velocities and the pressure in the flow field. Okay, so in that turbulent viscosity problems, actually what they do is that they express these Reynolds stress tensor term in terms of and turbulent viscosity and I guess the some sort of a kinetic energy. Yeah, so that's right. So they, like, what they do, they modulate using called the turbulent viscosity model. Okay, so in that turbulent viscosity model, actually you express this Reynolds stress in some equivalent viscosity, that is actually the molecular viscosity into average rate of deformation, and that quantity can be, so that means the last term, that is the dou xj of rho ui prime uj prime whole bar, can be written in terms of the turbulent fluctuating kinetic energy and an viscosity term, which is the eddy viscosity or the turbulent viscosity, and then you can model that term. And the other is the Reynolds stress modeling, that I will not go into the details of that. Okay, so I guess it's fine. In the next week I will try to solve few problems regarding that, or rather discuss few problems, and then move on to the next topic. Okay, so this is a very important topic, I should say, and all of you should know it very well. Okay, I guess fine. Okay, so again we will meet in the next week on I think it is 1st October. We will meet again. Okay, thank you.